Hi, I'm Amir Hossein Mirza Bozorg, and I'm going to talk about multi-point bending simulation by using a static general step in Abaqus CAE. This is the table of content of this video. First, I talk about types of multi-point bending test. Then I will talk about example explanation. Then I will talk about a step-by-step instruction of simulating 4-point bending test by using a static general step. Then I will talk about results discussion. And finally, I will talk about reviewing remarkable points. You can see that these are the schematic pictures of 3-point bending test and 4-point bending test. The methodology of FE simulation of each of these tests are completely similar. Therefore, without loss of generality, we will focus on simulating the 4-point bending test. In this video, the 4-point bending test of a steel specimen will be simulated. The cross-sectional area of the specimen is a square. The cross-sectional dimensions of the specimen is 0.1 meter. Its length is 1 meter. As the Young modulus of the rollers are much more than the Young modulus of the specimen, the rollers are assumed to be rigid. This is an acceptable assumption. The bottom rollers are completely fixed. The top rollers will move 0.1 meter downwards, so the specimen will deform. As this test is a quasi-static test, the static general step will be used. The friction coefficient will be assumed 0.2. This will not affect the generality of the simulation. You can see the model of 4-point bending test in the Abaqus CAE. These are rollers, 4 rollers, and this is the steel bar. In this slide, I have demonstrated the mechanical and physical properties of the specimen: density, Young modulus, Poisson's ratio, and plastic data. Because we are going to use a static general step, there is no need for using density and adding it to the definition of the material of a steel bar. This is the final FE model that the Abaqus standard solver will solve it. Now, according to the demonstrated data, I'm going to model the 4-point bending test in Abaqus CAE. In the part module, I will define and design roller and a steel bar. The modeling space is 3D. A steel bar is deformable and its shape is solid, and by using extrusion technique I can design it This is the approximate size of the sketch plane. I want to create the origin of the sketch plane. I'm creating the cross section of the steel bar. This is the steel bar. Now I'm going to create the roller. All of the rollers are the same. So I will create one roller and then I will use it for defining the other rollers in the assembly module. It will be discrete rigid and its shape is shell. This is a rigid part, so I will assign a reference point to it. I want to define the material of a steel bar. I'm defining all of the constants in SI units. Now I must define the section for a steel bar. This part is solid, so I set the category to solid. The roller is rigid, so there is no need for defining material and assigning it to the roller. Now I'm going to create the assembly by creating instances from the designed and defined parts. First, I rotate the roller. This is the assembly of the FE model. Now I want to define the step. The displacement of the top rollers is 0.1 meter downward. So we have large deformations in this model, and I activate the NLGOM. For having a faster simulation without convergence problems, I activate this setting too. For taking the reaction force of top rollers, I will define two sets from the RP of these rollers and then use them for defining history output for taking the reaction forces as a result. In the interaction module, I want to define the interaction property for the contact between rollers and the steel bar. Here I'm using the Coulomb formula for simplifying the way of creating contact interactions. I want to use find contact pairs tool. The red surfaces are master surfaces and the purple surfaces are slave surfaces. If you want to use surface to surface formula for defining contact and you are using Abaqus standard solver, the surface with finer mesh and with lower Young modulus must be the slave surface, and the surface with the coarser mesh and bigger Young modulus must be the master surface, like here. You can see the definition of these contact interactions. Now I'm going to define the boundary conditions. The rollers at the bottom are completely fixed. I select the RP of these rollers and I fix them. If you want to define boundary conditions or initial conditions for rigid bodies, you must define that boundary condition or initial condition for their reference points. I think that this size is a good size for the elements of the rigid body. For having accurate results, I determine to have 8 elements in this direction and as the steel bar has lower Young modulus, the surfaces of the steel bar that have contact with the rollers must have smaller elements. Now I'm going to create a job. Now the job is completed. I go back to the slide. Now I must talk about the results. I go back to the Abaqus CAE. This is the contour of von Mises stress. This is the contour of contact pressure. The areas colored in red are yielded, and now they are in the plastic domain. But these areas that are colored in blue are in elastic domain. Now I want to see the reaction forces. You can see that our problem has one symmetric plane, and theoretically the y component of the reaction forces must be equal, but here they have some differences. This difference is due to the numerical errors. Every FE simulation has numerical error. Now I want to talk about the remarkable points. In defining contact interaction by using surface-to-surface method, the correct selection of master and slave surfaces are very important. It has a direct effect on the accuracy of the simulation. The settings of the FE model must be as close as possible to the physical conditions of the real problem. Every assumption must be chosen wisely. The accuracy of the results completely depend on the local and global density of the mesh. An expert FE analyst must always know the sources of error in his or her simulation and recognize that whether the results have enough accuracy or only the trend of calculated curves are acceptable. You can contact me by using Telegram or WhatsApp or sending email to me. These are our services. Notice that all of our services are paid services and we do not have any free services. Thank you so much for your attention and concentration. Good luck.